Assalamualaikum warahmatullahi wabarakatuh. So today our group is going to present a project entitled Designing a Big Data Technology Architecture for Smart Agriculture and Crop Yield Optimization. Our group consists of 3 members. The first one is Ain Arisa, second one is Aina Adrina, and lastly Aisha Kamila. Alright, moving on to the introduction to agriculture solution. Paddy is Malaysia's most important food crop, but production is highly affected by climate change. Irregular rainfall, rising temperatures, droughts, and floods can significantly reduce crop yields. Most farming decisions are still reactive and made only after problems become visible in the field. There is no integrated system that combines sensor data, weather information, satellite imagery, and historical production records. Therefore, a big data solution is needed to provide early yield predictions and climate risk alerts for farmers and agriculture authorities. This problem matters to 3 different stakeholders. First one is farmer. Most paddy farmers are smallholders with limited saving. Unpredictable yields will lead to unstable income, and droughts and floods will cause major losses. Therefore, early prediction will help farmers to manage irrigation, fertilizer use, and also harvest timing. Second one is governments. Malaysia produces only 60 to 70% of its rice needs. Lower paddy production increases reliance on imports. A reliable forecast will help agency to plan subsidies, rice stock management, climate policies, support organizations such as MADA and KADA. Last one is for society. Since rice is a Malaysia's staple food, lower paddy production will lead to higher rice prices. Therefore, rising prices will affect lower income households the most. Early warning system will help to improve food security and farm productivity. Let's move on to input, sources, and process. This graph is taken from historical production from DOA paddy production by state 2016 to 2021. It is about weather data where MET Malaysia and NASA Power about rainfall, temperature, humidity, wind, and sunlight. And then the satellite imagery is taken from Sentinel-2 and MODIS, which is NDVI vegetation index will show crop health. And lastly, IoT field sensors, continuous soil moisture, soil pH water level, and temperature are shown in the graph. There are 3 big data challenges. First one is volume. The challenge is that thousands of IoT sensors, weathers, updates, and satellite images will generate a massive amounts of agricultural data over time, making storage and processing difficult for traditional single-server databases. So the solution is that HDFS will distribute storage across chip machines with redundancy, scaled by adding nodes, frequently use recent data live in NoSQL layer instead. Second one is velocity. The challenge is that field conditions can change within minutes, so delayed processing will make alert ineffective. Real-time monitoring is essential to provide timely irrigation and climate risk warning. So the solution is that a page Kafka stream sensor and weather data the instant it's produced, Spark streaming reads its very few seconds and trigger near real-time alerts. Lastly is the variety. The challenge is that structured stable, semi-structured JSON from different sensor models and unstructured satellite images or farmer nodes can be analyzed together without a common layer. Therefore, the solution is that a page NAFI, standardized timestamps, link sensor IDs to location, validates ranges, image also stay in HDFS, abstracted values such as NDVI to become structured records.
My name is Aina Adrina, and next I will explain the data storage and processing part of our proposed big data architecture. First, our system handles several types of agricultural data, including historical production and climate records, weather data, IoT sensor readings, and satellite or drone imagery. So, for data ingestion, we use Apache NiFi for batch data ingestion and Apache Kafka for real-time data streaming. So, for the data storage, HDFS is used as our historical data lake to store large amounts of agriculture data. Meanwhile, the MongoDB is used as an operational database for recent data and alerts. So next, for batch processing, Apache Spark analyzes historical data and trains our prediction models. At the same time, Spark streaming process real-time sensor and weather data generate alerts instantly. Now this slide shows the overall data of our system. For the batch process, historical yields records and climate achieved are first collected and sent to the Apache NiFi. The data is then stored in HDFS and processed using Apache Spark to produce yield forecasts and dashboards. So for the real-time process, IoT field sensors and weather or satellite feeds send data to the Apache Kafka. The data is stored in MongoDB and processed using Spark streaming. So the system then generates a real-time alerts that can be delivered through a mobile application. So the process data can be also archived in HDFS for further batch analysis. Okay, so this slide is present our layered architecture. First, at the bottom, we have the data source layer, which collects data from the IoT sensors, weather station, satellite imagery, and DOA records. Next is the ingestion layer, where Apache NiFi handles batch data and Apache Kafka handles real-time streaming. So the third layer is the storage layer, which uses HDFS for historical data and MongoDB for real-time data. Next, the processing layer uses Apache Spark for batch processing and Spark streaming for real-time processing. Then, the prediction layer uses machine learning models such as a random forest to generate predictions and support decision making. So finally, the analytics and visualization layer presents the result through the dashboards, mobile alerts, and reports for farmers and authorities. Then after processing the data, our system produces two main prediction outputs, which is the first is the district yield forecast, which predicts paddy yield in tons per hectare for each district. And these predictions are updated using weather, sensor, and historical data. So the results can support the planning of subsidies, rice stocks, and agriculture policies. The second output is short-term risk predictions. This predict irrigation needs and climate risk, including drought, food, and pest risk. These alerts help farmers make timely decisions and respond to potential problems before they become more serious. And next, I will explain the required data inputs for our prediction system. First, we need historical yield data, which contains the annual paddy production by state or by district. So this data can obtain from the Department of Agriculture through data.gov.my. Second, we need the weather data, including rainfall, temperature, and humidity. So the data can be obtained from Map Malaysia and NASA Power. So third, we require soil moisture, soil pH, and water level data from IoT field sensors. So these provide continuous information about the actual conditions in the agricultural fields. Next, we use the NDVI vegetation index, which is derived from satellite imagery such as Sentinel-2 and MODIS. NDVI helps us measure the crop health. So finally, we also need planting information such as the planting date, crop variety, and the planted area per season. This information can be obtained from farmers or agency records. By combining all these data inputs, the system has enough information to analyze the factors that influence paddy yield.
Now let's walk through how we actually turn raw data into yield forecast. In the 7-step pipeline, we start with the data collection, pulling in yield records where the archive, sensor logs, and NDVI vegetation data. Next, come in the cleaning integration where we feed gaps and faulty readings and join everything together by district and dates since our data comes from completely different sources. Once it's clean, we move to the feature engineering, shaping the same yield where the sensor and NDVI data into inputs that model can actually learn from. Then we do an 80-20 ratio trend or trace split so we can measure accuracy on data the model has never seen before. That fits into model training, where we train a random forest model on the training set. We then run evaluations, scoring the model with the RMSE and R-square to pick the best performing version. Finally, deployment and retraining. The model goes live to generate forecasts, and we retrain it every season as new data comes in, so it keeps improving over time. Next is suggested machine learning techniques. For the model side, we're proposing 4 techniques, each playing a different role. First is multiple linear regression is our baseline model. It is simple, easy to interpret, and useful for showing how individual climate factors affect yield. Next is random forest regression. It is our main forecasting model. It handles complex, non-linear relationships in data far better than linear regression, and it's what gives us our accurate yield predictions. Next is decision tree classifier. It handles risk classification, predicting irrigation needs, drought, flood, and pest risk. It's easy to explain, which matters a lot when farmers and officers need to trust and act on these alerts. And finally, XGBoost is our future enhancement. It's not part of the initial rollout, but as we collect more data over more seasons, it has the potential to push prediction accuracy even higher and can be adopted as the system matures. We move to the challenges and the solution. Of course, a system like this doesn't work in a vacuum. It has to survive a real-world condition in rural Malaysia. So here are 4 key challenges we identified and how we addressing each one. First is poor rural connectivity. A lot of paddy areas simply don't have reliable internet. Our solution is edge devices that store and pre-process readings locally. Sensing once connectivity returns, with critical alert also sent by SMS as a backup channel. Next is a sensor reliability, where IoT sensor degrade or malfunction over time. We handle this with the 95 validation rules that flag impossible values, cross-checks against nearby sensors and satellite data to catch faulty units and regular calibration schedule. Next is model drift under climate change. As the weather pattern shift, old models lose accuracy. So we retrain every season with the fresh yield and climate data, monitor forecast error over time, and add extreme event features like dry day streaks and flood accuracy. And lastly, cost and adoption by smallholders, where most paddy farmers can afford this infrastructure individually. That's why we propose shared infrastructure through MADA and CADA to spread the sensor cost, paired with the simple bilingual apps that deliver clear action messages through channels farmers already trust. To bring it all together, this project integrates NiFi, Kafka, HDFS, MongoDB, and Spark into one unified big data platform. What that means practically is that we are transforming scattered, messy agriculture data such as sensor readings, weather feeds, satellite imagery, and historical records into insight people can actually act on. The system delivers 2 things, which is paddy yield forecast at the district level and real-time climate risk alerts in the field. Together, this support better decision-making for farmers, managing irrigation and harvest timing for government agencies, planning subsidies and rice stock, and for policy makers shaping climate strategy. Ultimately, this is about promoting more sustainable and more resilient paddy production in Malaysia, helping the country reduce its reliance on food imports and protect farmers' livelihoods against the changing climate. This is all from us. Thank you.